we will discuss strong convergence. Let me recall what the strong convergence is. Okay. So we have defined it as a topology, but let me just recall what the strong convergence for sequences. So we have a Hilbert space H, then we have a Tn sequence in B of H. Then Tn converges strongly to P is in B of H. If Tn xi, it is just point-wise convergence. So let's discuss some properties of the strong convergence. So first statement is you have a sequence. This is only for sequences. This will not work for nets. Of course, strong convergence is a non-metriceable topology. It is actually metriceable on uniformly bounded sets. Okay, on bounded sets. I mean, bounded sets in operator this metric space. So if you have but in general, it's not metriceable. And if you have, so this will not work for nets. Okay? The Tn contained in B of H. And so then the following are equal. The following two statements. Then Tn converges to P strongly is equivalent to saying supremum, it is uniformly bounded. And there exists a set S contained in B of H, which is total. By total, we mean you take the span, that is, take the span of all elements in S and take the closure that is equal to S. And I mean, it is enough if the convergence happens in this set. So proof. Okay, I will just write the inequalities required for the proof and it will be clear. Okay. 1 implies 2. Of course, there is nothing unbig in this. It will converge. If the convergence happens for all elements in H, then it will happen for a subset. You only have to notice the boundedness, uniformly boundedness. Okay. So since Tn x xi converges to T xi for all xi, I mean for any xi, okay, this set Tn xi is bounded in N. Okay, this set. Okay. This set is bounded for all xi. Well, for any fixed xi, for any arbitrary xi, for all xi. Okay. Then can you say that? Can you say that supremum Tn is bounded? Do you know this theorem? That is precisely what is called. The question is, you have Tn xi converges to C xi. Okay, and this happens in H, which is of course a metric space. Okay, so Tn xi is bounded because it's a convergence sequence. Okay, from that, this implies supremum n norm Tn is less than infinity. Do you know this fact? Uniform boundedness principle. Yeah. This is called uniform bounded. Precisely, this is the statement. If it is point-wise bounded, then it is point-wise bounded in N, then the norm is also bounded. Okay? This is uniform boundedness principle. Okay? This is precisely what is called uniform boundedness. So 2 implies 1. And this is just, triangle inequality or something. So we have Tn xi converges to P xi for all xi in S. S is total. Of course, this implies this is just linear and addition. I mean, Tn xi converges to P xi for all xi in span of S, right? Okay. And by totality, span of S is dense there. So for eta in H, choose xi in closure of span of S such that xi minus eta is less than some, I mean, we will change this epsilon by something. Yeah. You don't need it, but here it is complete. Actually, you don't need, because I mean, you to prove it you need, but once it is proved, if you have something bounded, I mean, something is true on the, you can always extend. These are all bounded maps. You can always extend it, and the same thing will hold for the extension also. So you don't need to be complete. Here it is complete anyway. We are working only with Hilbert space always. And so now we want to consider this Tn eta, Tn eta, no? Eta minus T eta, so this is less than or equal to Tn eta, I mean, minus Tn eta. Maybe I will just directly write it as you. Tn xi minus Tn eta, which you can write it like that, plus Tn eta minus, sorry, eta minus xi, no? So eta minus xi. So this is xi minus T xi, Tn xi plus, I mean, it's okay. Tn, right? T xi minus T. Now you can make this less than epsilon, and this is bounded by something. Okay, so this is less than or equal to 3 mum over n. Is it okay if I write it like this? I assume you are mature and so this is just, so I have to write it from 2 steps. Okay, so this is less than or equal to Tn eta minus Tn xi. I'm taking it this and then taking the supremum also. Then this is Tn xi minus Tn xi minus T xi, and now you can make this less than epsilon and choose that epsilon less than this, if you call this k, this is less than epsilon by k and epsilon by this and all that. And so this is, you can make it less than okay, from k times epsilon if you wish. Last line, is not required. Tn xi, Tn eta minus, sorry. Yeah, it's supposed to be that. Sorry. I mean, I have a mind in this, because I've used xi here, I used. Okay. And the next statement is, okay, anyway, this is easy. We want to see we want to prove the following. If Tn converges to T strongly and some Sn converges to S strongly, okay, then Tn Sn, the multiplication is actually not jointly continuous with respect to strong topology. Okay, but you can disprove by using nets. But for sequences, it will work. Okay. For sequences, this will work. This doesn't mean multiplication is not, I mean, multiplication is actually individually, I mean, this is true. If Tn converges to T, then Tns will converge to Ts strongly. Okay, you can prove it. Similarly, the other way also, by the same kind of inequality. But it's not jointly continuous. Okay. If Tn converges to T, Sn converges, it will not imply that, I mean, if T lambda converges to T for nets and S lambda converges to T, we will not require that, but the product need not converge. But here it will converge strongly. For sequences, it will. So again, proof is again, I have to write just inequality. Tn Sn Tn Sn minus Ts xi is less than or equal to Tn Sn xi minus Tn uh, Tns, right? Plus Tnsj minus Tsj, which is less than or equal to supremum over n norm Tn. Of course, because it is converging, this is bounded. Smj minus Sj plus. So this is Tn up Si. It holds for all elements in H, so it will hold for this also, T up Si. And this goes to 0. Okay, so it's clear. So why we consider strong convergence is for the following theorem. Recall we defined a representation of L infinity X. So let X mu be a measure space. Then we had a representation pi mu tilde. Pi mu is defined for C of X, okay, where there is no measure. This is from L infinity of X mu to B of L2 X mu. Okay, you take the L2 X mu, which is the Hilbert space, and this is a representation. We proved that this is an isometric representation. Okay. Then we want to prove the following statement. Then Fn contained in L infinity and the supremum of Fn is bounded, is less than infinity, and Fn converges to F in measure. I will recall this in measure is equivalent to saying pi of Fn converges to pi of F strong. Pi mu. Okay. Where pi mu, okay, we were not there. Where pi mu tilde is a representation. Pi mu tilde of F is acting on, is an operator on L2, acting on G is just F. It's just a multiplication of it. Okay. You take the multiplication representation of L infinity, okay, then of course we have proved that it's an isometric representation, and I asked you to do something on the for the spectrum. So if the Fn converges to F in measure is equivalent to this, we want to prove this. But since you haven't seen convergence in measure, I will prove a statement about the convergence in measure, and then we'll come to this. Okay. It's true for I think it's true for general measure, but I will prove for finite measure. Okay. X some script F mu is a finite measure space. Okay. I will write the definition of measure. It will come there. I mean, I've already stated. I will recall it. So Fn converges to F. So Fn's are measurable functions. Okay, these are all just measurable functions. Fn converges to F in measure in mu. Okay. Implies there exists a subsequence. Subsequence Fn k such that Fn k converges to F mu almost everywhere. Okay. Actually, the other way, I mean, other way is true in the strong sense. If a subsequence, I mean, not subsequence. If a sequence converges to Fn converges to F mu almost everywhere, then it will converge in measure. But we will not need that. So we will need only this. Okay. Or you try proving that. It's very easy. So this direction needs something. That direction is easy. Okay. So I want to prove the following. I have functions, measurable functions. Fn converges to F in measure. Okay. Then I want to produce a subsequence which converges mu almost everywhere. So I have to produce a set A whose measure is 0, and in A complement, it should converge pointwise. Okay. That is what convergence convergence in mu almost everywhere means. Okay. So F1 converges to measure, F1 converges to F measure means that is this set mu such that all those x in x such that Fnx minus f of x greater than or equal to epsilon goes to 0 for all epsilon greater than. This is just the definition. This is the definition of convergence in measure. Okay. So I want to choose a sequence f and k. Okay. I have that condition for each epsilon. I have to choose a sequence. Okay. Choose f and k such that mu of, well, I want to sum something. So mu of f and k minus, I mean, I just choose f and k. Once f and k such that f of this set. I mean, when I write it, it's clear to you know. This means all those with x here. I mean, if I write like this is what it means. Okay, I will just write like this. Is greater than 1 by k is less than 1 by 2 power k. Okay, I choose an f and k like that. I choose nk like that. Okay. Okay. Then you call this set ak equal to this set. F1k minus f is greater than or equal to 1 by k. Okay. Call this set as ak. Then that 1 by 2k condition says that summation mu of ak k equal to 1 to infinity is less than, I mean, equal to 1, but less than infinity. See, have you seen something called Borel-Cantelli lemma? You have seen. That will use something called lim sup. That's what I will use now. Okay. So, I mean, this will show. Actually, that's what the proof I'm going to use. But I mean, if you go through the proof of that, that's what I will use. Okay. Then the lim sup of this set will have measure 0. That's what it means. Just more than something, right? Mu of ak converges to, this implies then mu of ak goes to 0, right? Not mu of ak, sorry, much more than that. That just this implies that mu of union k equal to n to infinity ak is of course less than or equal to summation k equal to n to infinity ak, okay, goes to 0 as n goes to infinity. Correct? Okay. Now this set you call it Bn. Okay. Bn is decreasing, right? Bn's are decreasing set. One is Bn is contained in Bn plus 1. Okay. So since mu is finite measure, for finite measure, this is true. If I have a decreasing sequence and Bn converges to some B, mu of Bn will decrease to B, mu of B. Okay. So Bn, I mean, so this implies mu of Bn, mu of intersection of n equal to 1 to m Bn equal to 0. Okay. You call this set as A. So I want to say that this f and k converges to f mu almost everywhere. Okay. So outside this A has measured 0. I want to prove that in A complement, point-wise convergence happens. That's what I want to say. And that is by definition, it will follow. So if x is in A complement, that is x is in So A is in, I mean, A is in the intersection of all this Bn. So X is in all those, I mean, X is in union of Bn complement. So there exists X is in A complement means the X is in Bn complement for some n. Some n. Okay. This n will work. What does it mean by convergence? Given epsilon, there exists n. After that, it should be, I mean, it should be less than epsilon. The difference should be less than epsilon. Okay. So X is in Bn complement for some n. So, I mean, what is Bn? Bn is the union of all these things. So Bn complement, the intersection of all those complements. So this implies X is in intersection of k equal to n to infinity, that An complement. An complement. I mean, X is in intersection means what? X is in AK complement. AK complement for all k greater than or equal to n. That's what it means. Okay. That is Fnkx minus f of x. So that is less than, that is greater than or equal to 1 by k. That is how the AK is defined. Okay. This is less than 1 by k for all k greater than or equal to. That's what you want. Okay. That's what you want. I mean, of course, this n will depend on x. If you want, you put a x here. Okay. Point-wise convergence. Okay. So now we will prove this theorem. Proof of proposition. We have already proved the following. We have proved pi mu is an isometric representation. Okay, it preserves the norm. We have proved Fn is in L infinity mu and supremum of Fn less than infinity, and Fn converges to F almost everywhere, mu, almost everywhere with respect to mu. Then, of course, this is just dominated convergence theorem. Then pi mu of Fn converges to pi mu of F, sorry, pi mu filter. Okay, strongly. We have actually proved it in the last class. So we are proving, we want to prove 1 implies 2. We want to prove 1 implies 2 in the proposition. We have a sequence which converges in measure, then we want to prove pi mu of Fn. I put a tilde, I'm sorry. I mean, it's okay, but this is on L infinity, you should remember. Okay, it's just multiplication. Okay, then pi mu Fn, this converges to this strongly. If the convergence happens in measure. Okay, but we have already proved if the convergence is in almost everywhere, then it converges strongly. Okay. So now suppose infinity and Fn converges to F in mu. So this is in bracket. We have proved this. Okay. Now suppose this is in, that is uniformly, the sequence is uniformly bounded and Fn converges to F in mu, then there exists a subsequence. Then there exists a subsequence which, I mean, let me just argue it out orally and then write it. Let me just be clear what to write. Okay. So if you have a sequence, which converges in measure. So that means it has a subsequence which converges mu almost everywhere. It says in particular, if you have a subsequence of Fn, which that will also converge in mu, of course. So Fn converges, I mean, by the definition, it's clear. Okay, if Fn converges to F in mu, then any subsequence will also converge to F in mu. Even though we haven't, I mean, We haven't proved that it actually arises from metric or something. In metric space, it's true, but here also it's true. Okay. So now if you have any subsequence, it will converge to F in mu. So it will have a further subsequence which converges of mu almost everywhere. Okay. So because of that, for any subsequence of Fn, there exists a further subsequence Fnk. Let me call that as Fnk. I take a subsequence, if I have a further subsequence, I call that as a subsequence as Fnk. I'm not writing that because there will be, I have to use two notation, Fnk. Then this converges almost everywhere. Okay, Fnk converges to F almost everywhere. That is pi mu tilde of Fnk converges to pi mu tilde of F strongly. Okay. That is, this converges to this for all psi in which. Okay. So this says that, so for any subsequence, should I write? I will not write it, I will just tell you. If you have any subsequence of this phi of Fn, right? Okay. Then it has, if you take any subsequence of this, then any subsequence of this admits a subsequence pi of Fnk xi converging to pi of F xi. This means pi of Fn will converge to pi of F xi. Okay. In a metric space, if you have a sequence such that every subsequence admits a further subsequence such that this happens, then the sequence will converge. Okay. You can easily prove. If this doesn't converge, then you will have a subsequence which will have a distance, strict distance, and that will not have a further, then you can easily prove it. Okay. So this implies pi of Fn xi converges to pi of F. That's what we want to prove. Okay, so 1 implies 2 is proved. 2 implies 1, we have. So suppose pi tilde pi mu of Fn converges to pi of F strongly. In particular, 1 is a finite measure. Okay, mu is a finite measure. Okay. We always consider finite measure. In fact, we will consider only probability measure. Okay, it will be, we will consider basically probability measure. Okay, measure of the whole space is 1. So 1 is in L2 X2. Okay, this implies pi tilde mu of Fn of 1. 1 is this vector. Okay, it is 1x. Constant function 1. Okay, 1x will converge to pi mu tilde of F1. Okay, this happens in L2. So this implies Fn converges to F in L2. Right? L infinity is contained in L2. It is in fact dense in L2, in the L2 now. Okay. So this just means integral over x Fn minus F square d mu goes to 0. Okay, as n goes to infinity. Now, mu of, we want to prove convergence in measure. Okay, so no mu of, actually it is also true if some convergence happens in L2, there is a subsequence which converges mu almost everywhere. We cannot conclude that this converges to this almost everywhere. That is not possible. But if convergence happens in L2, there will exist a subsequence. Okay. So this implies, but we don't need that. Okay. This implies mu of, we want to consider this set Fn minus F greater than or equal to F. That's what we want to consider. We want to show this goes to 0. Okay. Now this is equal to Okay, write it 1 by, this is less than or equal to, okay, 1 by epsilon square on G mu, where over this set. Okay, just by definition. Here in this set, this is greater than epsilon. You just integrate it over this set and divide it by 1 by epsilon. So this is true. And this is, of course, less than or equal to 1 by epsilon. So we have. So strong convergence imply convergence in measure is equivalent to convergence in measure for uniformly bounded sequence. So what is next? Okay, let's state the theorem. Let's recall everything. Okay, let's recall everything and state the theorem, and whatever is missing will prove. Okay. Okay. So first statement is. So Timothy, did you look at the videos or something? Huh? Huh? Okay. So we have defined some cyclic representation and all that. You know that. Okay. So I will not recall. I will just tell you. So the first thing we proved is, I mean, this part of the theorem. The first one we proved is, so you define pi mu from C of x to B of L to x. Okay. So which is just multiplication representation, pi 2 of g to G. Okay. Then pi mu is a cyclic representation. Of course, the representation, I mean, there's a star homomorphism and all that is a cyclic representation with cyclic vector, the constant function 1. Okay. Cyclic vector, so 1x. Okay. Second, we proved that if any pi from C of x to B of L2, sorry, B of h, if you have any cyclic, any representation is cyclic, then you, by using Riesz representation theorem, we proved that then there exists a mu. In fact, it is a probability measure actually, because you can take the cyclic vector to be unit vector, and this will give a probability measure if you go through the proof. Maybe I didn't mention. Okay. There exists a probability measure. Probability measure means measure of the whole set is 1. Okay. There exists a probability measure mu on x such that pi is unitarily equivalent. I mean, this is the only equivalence we deal with. So unitarily equivalent to pi. So we have proved this. Next step is we extend this statements to L infinity. Of course, L infinity is a bigger space, so it is again cyclic. We don't need to say that. Okay. We pi mu tilde, we have already proved pi mu tilde from L infinity x to B of L to x. Again, it's also multiplication representation. Fig is Fg. Okay. Then pi mu tilde is isometric, is an isometric representation. Pi mu tilde f is equal to norm f. This is the L infinity now. Okay. This is not C now. It's L infinity now. Okay. I mean, here you have a mu and here you have mu. They are the same mu. Okay. With respect to that mu. Okay. Okay. And then we proved that theorem. I mean, then we proved the following. Fn, you have Fn contained in L infinity, and Fn supremum. And Fn converges to F in mu. Okay. Then pi mu tilde Fn converges to pi of f. We have proved all that. Okay. Strongly. and pi mu tilde is the unique extension of pi mu. Pi mu, I mean, from C of x to L infinity. Pi mu is defined on L infinity. Pi mu tilde is a unique extension. Of course, clearly it's an extension because that's how we define. It's a multiplication. You only have to prove it's unique. Okay? So we only need to prove the uniqueness, which will follow from the following lemma. Yeah. Huh? What is compact? X is compact, yes. Yeah, we are working with X compact. Okay, always. We will be, I mean, our X will be a spectrum of some operator. Okay, so we are working with compact. So even if I don't mention, it's always compact. Okay, yes. So I may forget to say it's always compact, and measures will be finite measure and all that. Okay? And Hilbert spaces will be separable always. So all these things we assume. Okay? I mean, separability is important because we will have a countable decomposition soon, maybe in next class. In this class itself, maybe depending upon the time. Okay, so that's so. I mean, for that we need separability. Okay. So what is the lemma I want to prove? Yeah. So I want to prove the uniqueness that will follow from the following lemma. So for G in N infinity, there exists Fn contained in C of x such that Fn converges to G in mu in measure. Okay. You have continuous function. For an infinity function, you have continuous function converging to mu from there. Okay. Okay. Proof. You know, you told me that you know Lucin's theorem. Okay. Lucin's theorem says that, so you can, I mean, it's for Rn, but we will do it for, Lucin's theorem is for Rn. We use it for C, for same. It's the same thing, R2. Okay. Extend mu to C by taking 0 outside X. I mean, our X is contained in, assume, I mean, always our X is a compact subset of R2. I mean, you can work with all these things that we haven't used that anywhere. We have used only compactness. Okay, but we want to use it for spectrum. Okay, so assume that X is in, this is for, I mean, for this part, we assume that this is X is in contained in C. Okay? Because we want to use Lucin's theorem, which is for Rn. Okay? So extend mu to C by taking, I mean, by defining to be 0 for all subsets of X complement. Okay. Then for epsilon greater than 0, there exists continuous function uh, I mean, you don't need to extend, I believe, when this you can actually prove. Otherwise, you need some kind of, there exists continuous function f such that mu of f not equal to g, but g be L infinity. Okay. F not equal to g is less than epsilon. For each epsilon, you will have an f epsilon. Okay. Given a g, you have a continuous function. This is Lucin's. Okay. Right? Huh? We Lebesgue, only for Lebesgue measure it's true. It's true for finite measure, any radon measure, any finite regular nice measure. No. You proved only for Lebesgue measure?
Yeah, we use the regularity.
Yeah, regularity is true for any compact regularity. Any finite measure on a compact metric space is regular. You,
I think in R we use the regularity of the.
yeah, I'm using finite measure. So only by using the same regularity, you can prove it. You need only regularity, right? So, I mean, regularity is for any finite measure on compact. You know that, right? I think I gave a sketch orally. Okay. So by using that, you can prove it. Whether you look at the proof. Okay. Okay. So I want to choose for any n such that fn minus fn not equal to g is less than 1 by n. That's what I want to choose. But then those fn's may not be bounded. So one does the following. So let r be the function from c to c itself, c to r, c to c, where r of z equal to z and r of if norm is mod z is less than or equal to, I called it g, no? So, okay, it's okay. Lucian's theorem says that if you have any measurable function, I think any L infinity function, then you have a given epsilon, you can find a continuous function such that where they don't agree, measure is less than epsilon. Okay. I think it uses, there is something called Agros theorem, which says that given epsilon, you can always, I mean, if the convergence is almost everywhere, given epsilon, you will find a set where the set is less than epsilon. The measure of the set is less than epsilon. The convergence will be uniform outside that set. We can do it sometime if you want to go through those things. Okay, I mean, or you can do it. Okay. So for mod is less than or equal to norm, let me call this phi. Okay, because I want to choose g. G epsilon such that g epsilon not equal to phi e in p. Okay. And r of z equal to, you just I mean, you just, it becomes norm phi infinity. So z by, see, you have a some continuous function on real line. It reaches a bound m. After that, it is just constant m. Okay, but here it's a complex plane. You have to consider this radial. I mean, this what is it called, amplitude. Okay, it's something like this. You have a function. Okay, it takes some value, and when it reaches that phi infinity, okay, you take the, you just take this. What is it? Z by norm is, what is it called, amplitude. whatever. This thing times phi infinity. Okay, so that it's bounded. Okay, it's still continuous. This function is continuous and bounded. And take f epsilon equal to r of g epsilon. R of g epsilon. This is just to make it bounded. That's all. Okay. This is that e power I theta part. That's all I said. Okay. Then mu of this set g not equal to p. Okay. This is contained in mu g not equal to f not equal to, no, this I have taken f, no, F epsilon, okay, not equal to phi, same as is contained in G epsilon. Okay. See, if F epsilon is equal to phi, in particular, I mean, phi is always less than or equal to phi is, notice that phi mod of phi z is always less than or equal to norm phi. Okay, almost everywhere outside a set of measure 0. We are only consider mu. Okay, so set of measure 0 doesn't matter here. Okay, so we are only using the mu part, actually not set inclusion. So this is less than or equal to not inclusion. I mean, on the set of measure 0, anything can happen. We don't care. Okay, so when f epsilon is not equal to, when f epsilon is equal to phi, it will be phi. I mean, this f epsilon will be less than that phi infinity. Okay, if f epsilon is equal to phi, then f epsilon will be less than or equal to phi infinity, right? That's how it's defined. So when this is not equal to that, okay, wait, is true. I want to say that G epsilon not equal to. Is that right? The statement. Eh? No, G epsilon may be unbounded. No, this is bounded. F epsilon is bounded. G epsilon may be unbounded. We are originally choosing what is given by Lewis' theorem may be unbounded. No, G epsilon can be unbounded, maybe not on emission 0. G epsilon. This is F epsilon will be bounded. Okay? G epsilon may be unbounded. So in that, when F epsilon, I mean, when F epsilon is equal to phi, that G epsilon is also same thing. It's the same set. F epsilon equal to V is G epsilon equal to. Okay, so this is less than epsilon. Okay. So now choose Fn such that mu of Fn not equal to phi is less than 1 by n. So in particular, mu of Fn minus phi greater than or equal to epsilon 1 by n. Okay, will go to 0. Yeah. I mean, sorry, greater than epsilon will go to 0, less than 1. Fn minus phi greater than epsilon is certainly a bigger set than Fn not equal to phi, right? Huh? I mean, this set is contained in the, sorry. This set is less than or equal to mu of Fn not equal to phi, right? Fn not equal to phi, Fn equal to phi means Fn minus phi is 0. So this set contains this, right? And this set is less than 1 by n, which goes to 0. Okay. So we approved it. Okay. So there exists a sequence continuous function, which converges in measure to G. Okay. And so because of that, it's clear. I mean, it has to be, multiplication is jointly continuous. Sorry, multiplication is continuous with respect to strong topology. From that, it follows. The proof of the theorem, if you want. Proof of that is theorem, no? Proof of theorem. There exists Fn contained in C of x such that Fn supremum of Fn. So if you have a phi in an infinity, okay, then supremum of Fn is less than infinity, and Fn converges to F in mu. Okay, this implies pi of Fn, pi mu of tilde of Fn converges to pi mu tilde of phi. Okay, pi mu tilde of phi. But then in strong way, this just means that pi mu tilde of, this just means that Fn xi converges to phi xi for all xi in L2. But then, Is it clear that pi mu is I mean, this, I mean, then there cannot be two extensions. Okay. What do you want to say? I want to prove the uniqueness of this pi mu delta. Okay. So suppose, okay, I should have said this, sorry. I mean, this is the suppose pi is any extension. Sorry, I should change all this. Any extension of pi mu on C of x. Let me start everything again. Okay. Suppose pi is any extension of pi. We have pi mu, which is the multiplication representation of C of x. Suppose pi is any extension of pi mu on C of x. Now you take count பண்ணாதீங்க, சைலண்ட்ல போட்டுருங்க. So pi is any extension of pi mu on Cx. Okay. So we want to prove that this this extension pi is nothing but pi mu delta. That's what we want to prove. We want to prove the uniqueness, right? So we want to prove pi equal to pi mu delta. Okay. So suppose you have take any phi in this. Okay. Now because of, I mean, pi mu delta satisfies all this. It satisfies all those conditions. Okay. So you take, so now you take any fn such that supremum fn is like that. Then you have pi of fn converges to pi of this, pi mu of this. Okay. But then this pi is an extension of that. So this implies pi of fn acting on any g is equal to, silentல போடுங்க please, இல்ல ஆஃப் பண்ணிடுங்க. Right? Okay. So this implies, I just want to say that pi mu delta of fn p, and this converges to pi mu of phi at g for all g in L2. Okay. This implies pi mu of phi at g is just pg. Right? Because of this condition. Anyway, convince yourself. It's clear. என்ன ப்ராப்ளம் உங்களுக்கு? Okay. Any confusion? I'm sorry, I get distracted from that. I want to prove that pi is the, I mean, pi is any extension of pi mu. Pi mu is on Cx. And I want to prove pi is equal to pi mu. Okay. I have continuous functions fn converging to phi in mu. That's what I have. Okay. Then by the property of this pi of fn will converge to pi mu of fn strongly. But then phi of fn acting on g, because fn is in C of x, that is equal to this multiplication fn times g. Okay. Fn times g will converge to phi g. So because the limit is unique and all that, pi mu of f, pi mu delta of pi, I mean, pi of fn will converge to pi of, sorry, pi of phi. Okay. Then pi of phi is also equal to phi g. This is okay. You just argue to us. Okay. There is nothing complicated. Okay. Before stating this theorem, so have you seen direct sum of Hilbert spaces? I believe you have seen direct sum of Hilbert spaces. You have H1 direct sum. Direct sum of vector space, you know. We discussed this direct sum in the first class, internal direct sum, external direct sum. So direct sum of vector space, you just take tuple x, y, and then, I mean, anything in this can be uniquely written as x plus y. So external direct sum H2 is just the algebraic direct sum. You take the algebraic direct sum and you define the inner product between x1, y1 and x2, y2, or you usually write it like this. Okay? I mean, the tuple, you just write it like this. Okay? Y1 direction by. This is how you write this. This is equal to summation x1, y1 plus x2, y2. You can verify this is an inner product. And this x1, h1 and h2 will sit as subspaces, and they will be orthogonal in this new inner product. Okay? You can do the following. Hn be a sequence of Hilbert spaces. You don't need sequence. You can actually take an uncountable or arbitrary one, but then you have to, then you can't concretely define. I mean, then also you can do it. I will come to that later. I mean, that's not needed for us. N in N. Any sequence of Hilbert spaces, countable sequence of Hilbert spaces. Okay. To define H equal to all those xn is in H. To take all sequences. Okay. This is your H, such that summation norm xn square. Fine. Just take L2 sequences like this. Okay. Then H is a Hilbert space. With respect to this xn, yn equal to summation. This is of course well defined by Cauchy-Schwarz inequality. I mean Cauchy-Schwarz inequality for 2A, Cauchy-Schwarz inequality in L2 and Cauchy-Schwarz inequality in each Hn. Okay. So this is assignment. I want you to write it. I mean, it's better you do that since you haven't done it. So this is assignment 1. The assignment is to prove that this is a Hilbert space. First, you have to verify that this inner product is well defined. Okay. Where it's well defined inner product, and then it's a Hilbert space. And the proof of the Hilbert space is same as proof that L2 is a Hilbert space. Okay. So 2 this is also part of assignment. Okay. If you have operator T in B of Hn, okay, such that supremum n of norm Tn is less than infinity. Okay. So I don't want to write it like that. I usually write usually write it as direct sum of xn. Okay. For any sequence such that the summation xn squared is less than infinity, I write it like that. Okay. So I have a sequence of operators Tn in B of Hn, then define direct sum of Tn, n equal to 1 to infinity Tn, acting on direct sum of xn and xn. Okay. Then n equal to 1 to infinity, okay, equal to just Tn xn. Okay. Is a well-defined bounded operator, which is very easy to verify. Okay. Such that norm T, I mean, this is not okay, norm of Tn n equal to T. Okay. This direct sum is equal to supremum is equal to this. I will tell you how to do that. First, you want to prove that this norm, I mean, you prove that bounded, I mean, that follows from this argument. So you want to prove that this norm is equal to this. Okay. So if you take, I mean, you take any L2 sequence, you can multiply with the L infinity sequence, the small L infinity, bounded sequence. If you take an L2 sequence xn, you can multiply by a small L infinity sequence. Then this L2 norm of this sequence will be less than or equal to, I mean, same as integral. Norm yn infinity times this. You can do that, right? If you have an L infinity, if you have L2 sequence in L2, okay. I mean, here also it comes from the Hilbert space, but it's like L2. Okay. So if you have an L2 sequence, you can multiply by a bounded sequence, L infinity sequence. By taking out the norm of that, you can do that. Okay. So this is the L infinity norm of that sequence or something. So similar to that, you can take it out using the same norm inequality and all that. So first, so you can prove that norm of this is less than or equal to this. So now we want to show that the supremum is actually attained. Okay. First, you argue that this is the supremum of all those numbers. So given epsilon, you will find a Tn such that norm Tn is greater than that supremum minus epsilon. Okay. For the norm Tn, you will find a vector, unit vector, which will approximate that norm. So by that, you will show that this norm can be approximated by this acting on a vector. You have to argue it something like that. You have given the argument. Okay. So you prove that norm is equal to this. The assignment is clear, no? So this is the Hilbert space, direct sum of infinite direct sum of Hilbert space, countable direct sum of Hilbert space, which is defined like that. Show that it is a Hilbert space, and you can define direct sum of operators like this. And the norm of that operator is equal to this. Here, phi from C of x to B of h be any representation. Because I have said earlier, we have assumed this, we assume that H is the Hilbert space. I should have said no, but I said there won't be any sound, so I allowed him to do this. So sorry about that. Anyway, we are going to end. So be any representation, then X is compact. X is, if you want, you consider it a subset of C. Okay, then there exists a sequence of measures, sequence mu1 n in n of probability measures on X such that pi is unitarily equivalent to direct sum of pi mu n. You know how direct sum of representation is. You just take the direct sum of operators. I mean, if you have a pi n from C of x to some B of Hn, okay, then you take the direct sum of Hn, okay, B of this, and you define a direct sum of pi n from C of x to this. But of course, direct sum of pi n of any function is going to be direct sum of pi n acting on any function is direct sum of pi n f. I mean, just directly. This direct sum is a single thing. You call it pi or something. Okay? Pi of f acting on the direct sum is just direct sum of, these are all operators. To take direct sum of all these. So this is well defined. So given any representation, you have a sequence of probability measure such that pi is unitarily equivalent to pi mu. This is John's lemma. Okay. So First, we want to prove that we are given a representation phi, which is arbitrary representation. So we want to write it as direct sum. I mean, first, any representation can be written as direct sum of cyclic representation by Zon's lemma. So that we want to prove. And any cyclic representation is given by a pi. That's all. Okay, that's what you want. Okay. So consider this sequence. Consider this collection. How do you write the collection? C equal to direct sum of Hn, okay, Xi n. So where all this tuple direct sum of Hn Xi n is okay. Where Hn is contained in H and Xi n in Hn a unit vector, okay, such that pi restricted to this Hn. I mean, pi restrict to well, the statement implies all that. Pi restrict to this, all that. Okay? Pi restricted to P of Hn. Pi restricted to, sorry, such that, I mean, how do we read? Pi of f in C of x. Okay? Pi of f as an operator, you restrict to this Hn. Okay? It's a cyclic representation. And Hn is orthogonal to Hm if n not equal to m. I take orthogonal collection of Hn, each has a Xi n, okay, such that if you restrict pi, I mean, not that you can always restrict, it may take it outside. Okay, so, okay, let me write it. Hn can, okay, let me write. Hn contained in H is invariant for pi of f for all f in C of x. Okay, this makes sense. Okay, and Xi n in Hn is cyclic. Okay. Cyclic for pi restricted to, I mean, pi of f restricted to Hn. This is okay, no? And there is a notation is not clear, but what I have written is clear. Okay. Hn is a subspace and it's an invariant subspace. It takes element into itself. Okay. It's an invariant subspace. And you take that collection and so that it's cyclic. That is pi of f acting on Xi n. Okay, and take the span closure is equal to Hn for f in C of x. You take f in C of x, pi of maybe take this closure, that is equal to Hn. It is just Hn is invariant and Xi n is a cyclic vector for the restricted representation. You take that collection of this Xn. Okay, and you argue that any totally ordered set will have an upper bound. Okay, you take the, I mean, Hn and Hm are orthogonal. Okay, now if you have a what is it, totally ordered set? If you have a, what is it called? I forgot. Zon's lemma, what is the statement? What is that statement? Chain. Okay, that's the word. Yeah. If you take any chain, you can take the union of all those things, union of the collection. Okay, I mean, one is contained in the other. Okay, that will be at most countable. These are all countable. So that will be, I mean, this may be a countable set. Okay, I mean, but this is, I mean, for n equal to 1 to infinity, I have written because it's countable. Okay, so that will be countable, and that will be again, again that's again, I mean, that will have an upper bound. Every chain will have an upper bound. Okay, so you will there exists a maximal element. The point here is, if you have some Hn is invariant, I mean, by invariance I mean that pi of f of xi some eta in Hn, pi of f xi eta is also contained in this. It will take the orthogonal complement is also invariant. That is because you know that if you have T is invariant, I mean some subspace is invariant under T, and the orthogonal complement is invariant under T star. Here it is invariant under all pi of f. So pi of f star is pi of f bar. Okay, so orthogonal complement is also invariant. So because of that, if you have a maximal element, then the direction should be equal to h. Okay. So this admits a maximal element. Admits a maximal element. Okay. Maximal element, say Hn xn. Okay. I mean, I'm not writing it. It's clear to you, know. Then direct sum of Hn is equal to h. The point is, you cannot have, I mean, the direct sum has to be countable, because if you have a separable Hilbert space, then I mean if you have a set of orthonormal set, that will be countable. I mean, any orthonormal set will be countable. So orthogonal subspaces should be countable, of course. Okay, so it will be at most countable. So then n equal to 1 to infinity Hn should be equal to. So we have proved that we have decomposed H into direct sum of Hn, which are cyclic, and each Hn is actually equivalent to some pi mu n. I mean, each Hn, pi restricted to this Hn is actually equivalent to pi mu n on some L2 something. Then the direct sum is also equivalent, because if you have a unitary operator intertwining that, you either write it or then, I mean, it's all clear. If you have some un intertwining one pi and pi n and pi mu n, the direct sum of pi n will be intertwined by direct sum of un. Direct sum of un is again a bounded operator. If you have unitary operators on each Hn, you can define the direct sum of un and the direct sum of Hn. Okay, that will again be unitary. That's clear, no? Because it preserves the inner product. The inner product is just summation of all those inner products, right? So it will preserve each one of them, so it will preserve the inner product also. All these things are clear. Okay, so this theorem is clear, I'm saying. Hn?
Hn and Hm are like orthogonal and not.
Yeah.
Like, are we talking about any two elements?
No. Within this, this is a collection of Hilbert spaces, collection of xi. Okay, within this Hn and Hm, this is a sequence, maybe finite. Okay, it's a sequence. In the sequence of Hilbert spaces, Hn and Hm are orthogonal, and each one of them is cyclic. Order. This is contained in that bigger one. That's all. You have a bigger, this set Hn, that's a bigger collection. That's all. The totally orderedness in this that's a bigger collection. I mean, this is contained. This is less than or equal to another say kn, km xi eta m. Okay, if this Hn xi m sits as some element there, that's all. Just inclusion of sets kind of. Okay, it's okay, no? Yeah. Then that will have a maximal element. Then every chain will have an upper bound. That will have a maximal element. Yeah. Yeah, you can take it. It's not required, but it's okay. You can take it. Yeah. No, you have one collection. This collection is contained in the other collection. Okay. Then every chain will have a maximal element. That's clear. You just take the union of that collection. Okay. So one is contained in the other. I mean, one either this way or the other way. They are included here or included there. So you take the union. So that will be a collection. So that will have a maximal element. So the direction should be equal to H. That's all. Yeah. Okay.